Analytical Chemistry 1, Lesson 34. As mentioned earlier, there are 7 of the common amino acids which are actually triprotic. There's a third acid-base site in the molecule that is located on the substituent side groups. 3 are basic in nature, while the other 4 are acidic. Let's see how our work with the diprotic species can readily extend to the triprotic variety. And a reminder that we are using amino acids as examples of multiprotic acid-base systems, but all of the developmental work we do here can be extended to other polyprotic systems, organic and inorganic. So let's use aspartic acid as our triprotic example system. Aspartic acid has an acetic acid moiety as its substituent side group. The 3 pKa values that characterize this molecule are 1.990, 3.900, and 10.002. The first is for the proton on the carboxylic acid group next to the amine. The second is for the proton on the carboxylic acid group on the substituent. And the third, of course, is for the proton on the amine group next to the carboxylate. And there are 4 molecular species that arise in this acid-base system. I use the abbreviation ASP, ASP, for the aspartic acid moiety. The fully protonated form carries a +1 charge on the ammonium site. I call this species H3-ASP+. The first proton removed is from the alpha carboxylic group. The species is zwitterionic, though the net charge is 0. Part of the time it may be the neutral species that is used as the common molecular representation, so I call this species H2-ASP. The other carboxylic proton is removed next. For H-ASP-, the net charge is now -1, though the one labile proton likely moves around a lot. The fully deprotonated species carries a -2 charge due to the 2 carboxylate anions. It is labeled Asp2-. And there are 3 acid reactions and their corresponding 3 base reactions that connect these 4 species with each other. Here are the 3 acid dissociation reactions, along with the assignment of the various acid dissociation constants. And the corresponding base hydrolysis reactions are here, as are the assigned base hydrolysis constants. And a reminder of the relationship between these acid and base constants. One needs to be sure that they use the reactions that are interconnecting the same species. The concepts that we reasoned out with the diprotic molecules apply the same way here. We should be able to jump right in and describe how to calculate the pH of a solution formed by the addition of any of the 4 potential species. First, consider a solution whose formal concentration is 0.025 molar in aspartinium hydrochloride, or the H3-ASP+ species. This is the fully acidic species. Like the diprotic species, we treat it as a monoprotic acid, assuming that the other reactions are negligible. We use the same quadratic formula equation to find that the pH is 1.932. At the other extreme of pH is when a 0.025 formal solution of disodium aspartate is dissolved in water. This is the fully basic species, the fully deprotonated species. We treat it, as we did in the diprotic case, as a monoprotic base and assume that the other reactions are negligible. Use Ka3 to find Kb1. The quadratic solution finds the hydroxide concentration. Get the pOH and subtract from 14 for the pH. Now this approach works fine for the fully protonated or fully unprotonated species. What about the 2 intermediate species? First, we can consider a 0.025 molar solution of H2-ASP. It is amphiprotic and can behave both as a base, converting to H3-ASP+, or as an acid, converting to H-ASP-. We make the same analysis and arrive at the same conclusion as before. We will assume that the formal concentration is the species concentration for H2-ASP. This allows us to find the hydronium ion concentration using the same expression as before. But if you recall, we cast that equation in terms of the 2 acid dissociation constants for the 2 reactions. The one that produces H2-ASP is Ka1, and the one that consumes H2-ASP is Ka2. So while we could determine Kb3, we do not need to. Just leave it as Ka1. We find the following. The hydronium ion concentration is 9.56 times 10 to the -4 molar, so the pH is 3.02. The next intermediate species is H-ASP-. It could be delivered to the solution as sodium aspartate. There are again 2 reactions, but keep the constants as the 2 acid dissociation constants. Our equation is set up to work in that manner. Again, the formal concentration is 25 millimolar. And we make the same approximation, equating the formal concentration to the species concentration of H-ASP-. Plug all this into the equation to solve for the hydronium ion concentration. The hydronium ion concentration is 1.12 times 10 to the minus 7 molar, so that the solution pH is 6.951. Now, do you remember that with the intermediate species, there was an additional approximation, the average of the two pKa's involved in that species reactivity? We can use this as an easy check on our calculation. For the first one, H2ASP, the average of 1.99 and 3.90 is 2.945. It's pretty close to our value of 3.02. And for the second HASP minus, the average of 3.90 and 10.002 is 6.951, exactly the same value as our more complex calculation. Here's a summary of how to deal with solutions formed by the addition of any form of a polyprotic acid. The fully protonated form, here's the quadratic expression along with Ka1. Each intermediate species, use this expression using Ka of I or Ka of I plus 1. Substitute the formal concentration for the species concentration. Check your result by comparing it with the average of pKa of I and pKa of I plus 1. Be sure to take the average of the pKa's and not the Ka's. You need to take the square root of the product of the Ka's if you want to do it that way. And you do this for each intermediate form. Finally, the fully deprotonated form is analyzed with the quadratic expression using Kb1, which has to be found from Ka3. This gives you the hydroxide concentration, or the pOH, which can be turned back into a pH when needed. A reminder again that these equations, along with these assumptions and approximations, can be used with any polyprotic species. For instance, phosphoric acid, H3PO4, is a triprotic organic acid, and the approach can be extended to species with even more acid-base sites. When we start talking about complex ion formation, we will encounter a molecule abbreviated as EDTA, which has 6 acid-base sites. The fully acidic and the fully basic forms are treated with the quadratic equation, and all intermediate forms use the approach as above. Just be sure to use the correct pair of Ka values for each species.